Okay, great. Good morning, everyone. So to get started, we're going to focus on prepping for Lab 6, go through DML operations, and then start talking about DDL operations, which is create and alter command. That is something we need to know when we work with Lab 7. So jumping on to preparing for Lab 6. So Lab 6 is about relational database design. And this is up and coming, due this coming week. If I check the dates on the website really quick, Lab 6 is due on March 5th. So that's a week from today. So when we're doing relational database design, we have to factor in a few things. You're going to have to learn the RDBMS basics. You're going to have to focus on set theory. This is a minor part of database design because it helps you logically organize your sets. And then we have to look at entity relationships and the representing design graphically, which is either using the crow notation. So we can use either crow notation or UML. So there is, of course, a process to this madness of doing database design. And the process is understand the requirements, then define the entities, describe the relationship between entities, and then diagram it. That's generally the process that I end up following. Now, defining the entities is where we basically, when we review the requirements, any entity definition is generally from the requirements. Things that can stand on its own is generally defined as an entity. So when you look at assignment 6, which says the following: Dean of Admissions at De Anza College has hired you to do a database design for their registration system. College then becomes one entity. And keeping in mind the following requirements, design a database schema. College has several departments. Departments has courses. Courses have sections. College has locations. So each one of these, in my mind, is an entity. Like college becomes an entity, department becomes an entity, courses, and then sections, even locations. So generally, this is when I'm going through the requirements. This is how I come up with the entities. And then there is students. They register for classes. So we have to define that too as an entity. Students have to pay they have to pay for taking the course. So for this particular purpose, we may need some table called tuition. So there's also instructors teaching the section, which is not incorporated here, but that's another entity that will that'll need to be added. Instructors teach a section. Now somebody had brought up a question about section, like what is the difference between a course and a section? So a course would be something that is a subject that is taught, and when we talk about a section, it is an instance of a course that is taught. So at a given time, location, and by a specific instructor. So there will be a relationship of containment, or section will be linked to courses. Course will end up being a parent, and section will end up being a child. So as I'm looking through requirements, the first thing I want to do is come up with all the possible entities that are generally defined by way of making sure that each entity that is described can stand on its own. And then later in the game, we may end up defining other entities to take care of dependency between different entities, or to take care of relationships, to take care of multiple relationships between different entities. So this is the first step in the database schema, is understanding the requirements. Once you have enumerated all the requirements or gone through the requirements and you have described the entities, define the entities, then it's time to describe the relationship between those. So basically, in this step, we will enumerate all the entities that a given system will need. Then the third part is describing the relationship between entities. So this requires going through Intro to RDBMS. This requires knowing what is a relational database, what is a primary key and a foreign key, and this also requires knowing the rules of normalization. So as long as we know these three things, I think we are in good shape. And there are three rules that we are going to end up applying. Three rules that you'll end up applying. So what is a relational database? Well, a relation is called a table that has rows and columns. Relation is a table that has rows and columns. And then they are linked with each other through logical relationships referred to as primary and foreign key. So primary key is essentially a unique value assigned in a table. So it's a unique value assigned in a table. So every column in the table every other column in the table can be dependent on the primary key for its uniqueness, for the uniqueness of the row. So every other column. So that basically means that if I create a table called employees, which is what we have been using, employee ID will be the primary key. And that means that the different attributes in employee table, like name and location and address and title and salary and all that, can be managed easily. So anytime we refer to a unique employee ID, we can get all the information. So, and we also end up creating foreign keys. Foreign key is a way of bringing information from other tables into the child table. It's bringing information from other tables. So if I make department ID as a foreign key, then I'm basically bringing in all department information into employee table. See, the thing is that we are trying to avoid duplication. We're trying to avoid duplicating same data in multiple tables. So let me give you an example of that. Another example. So let's say you have a customer table, and customer can have multiple addresses. So you come up with ID, name, street number, street name, and city and zip code, city, state, and zip code. And then it turns out that you want to save one more address for this customer. So another thinking would be that we just add another set of data to handle multiple addresses. So we can do this all day long, just keep adding more columns. And that is the duplication of information in the same table that we are trying to avoid. Duplicating same data, or I should actually restate this, duplicating similar data in same table. So instead what we do is, so this would be essentially a bad design. So what we do is instead is we have a customer table, and we have a address table. So if one customer can have many addresses, then we will create a relationship between those two tables. So if we say customer has multiple addresses, so we'll say address 1 or address ID and all this. And each address can have a customer ID as a foreign key. So customer can have other properties like ID and name and total sales or customer SINs. So all this information can be easily tracked. So by adding customer ID, this becomes the foreign key, and we are not duplicating information anymore. For each row in the address table, we can basically say, for each row in the address table, we can simply say that that address it belongs to a customer. But here in the customer and address association, so in this association, we have to be careful. If we are looking at we have to look at the cardinality, which refers to the numeric association, like numerical association between two entities. So it can be like one address or one customer has many addresses, or one customer can have only one address, and then one address can belong to many customers. One address can belong to zero or more customers. So this refers to the cardinality, and we end up determining this for each relationship that we set up in our we end up looking at this for every relationship we set up in our schema. Is this making sense, folks? Any questions from anyone? So once we have determined entities and this primary key foreign key relationship and the cardinality, we are then in a good shape to draw out the schema. For views, we write a select statement. So we are not exactly creating primary key and foreign key relationships. So when you create a view, you are simply representing. When you're creating a view, you're just writing a select statement. So there, the rules of primary and foreign key do not apply. Okay. So there is one more thing, which is learning rules of normalization. Relation between catalog and other entities. Those are generally not created because a table physically lives in the database. View just lives. View is just view is compiled when you use it. When you do a select and so on. So you cannot create primary key foreign key relationship with views. You can only do that with tables that actually live in the physically in the database. So relationships are not created between views and other entities. To answer that question. So there are rules of normalization. Sure, no problem. If there's more, I'm happy to, of course, address it. So I want to refresh your memory on rules of normalization. And for that, I'm going to just cite these three normal forms. The first one that you can see here is, it says that the arrays and other repeating fields should not be used. So this was what I was trying to say with addresses. So we'll put that out here just in your notes for your reference. Number one, do not use repeating fields. Anytime you see column names being repeated, it's an opportunity to create a new table. So the word normalizing is often used to essentially take a schema and bring it in line with these rules. So, okay, do not use repeating fields. So we'll create a new table for normalizing those repeating fields. The second rule, second normal form, is that you should avoid unnecessary duplication of data. All of the data should be dependent on the primary key. So that basically means that every table should have a primary key. Every table should have a primary key. And then the third rule I mean, there's more examples described, but I'm ignoring those. Columns must not be interdependent. That's the third rule. Each of the columns in the table should not be interdependent. So that means no calculated columns, like salary times 1.10. A calculated value like this should not be stored in the database. Okay? Calculated value should not be stored in the database, because it can just be, you can just bring it up in the select statement. And the second thing is, you also don't want to duplicate information across tables. That's what that part is saying. You don't want a table to contain information that's already defined elsewhere, which can be calculated from existing values. So no calculated columns, and I'd say that I'd like to put these as separate points. No calculated columns, and avoid duplication of data across tables. So like adding address for student entity and instructor entity in different tables. What we can do is create a student table, an address table, and instructor table, and link those, rather than create information in one place, like rather than duplicate information. So this is also referred to as normalizing. So in cardinality setup, we often talk about 1 to 1, 0 to 1, 1 to 0, 1 to many, many to 1, and then many to many. Is this part clear, everybody? How the cardinality linkage is to be added? Okay. So we take sum total of all these ideas and we basically design a schema. And schema is nothing but a group of tables created using a specific ID in a database. We can say group of tables and objects. Okay? So what I've done is, in lab 6, I've provided this text file which you can consider looking at as the basis for learning how to design. So of course let me increase the font size just so it's readable for you all. So you can see the requirements that we talked about earlier, right? So those requirements are of course still the same, and what I've done is come up with all the entities and their respective attributes, and I've also defined if a table will be a parent or a child to start off the idea on how the relationships might be set up. So what I'm saying is let's create a table called a user, in which we are going to define the ID, their first and last name, address, email, and so on. Resident ID is the foreign key. So you see how we have resident table right here. So this will end up being the foreign key. Resident ID and type. Type is talking about whether it's an instructor or a student. So you can say, you can either spell it out or you can say 0 or 1. So depending on the data type you'll end up using. Then we have our second table, location, that just has a ID and a name. We can also add the address of a location, but you know, I chose not to get so detailed in this design proposal, but if you end up adding an address, you can certainly do that. Then we have payment, which is another table that describes the different payment types. So we'll have ID and payment name. So we can say payment name is Visa, MasterCard, cash, check, whatever. So that way we can, when we have to say that a student is going to pay with a specific payment, then we can refer to it here from the payment table. The other table is residency. If a student is resident or non-resident, they pay there's a different fee schedule. And so if a student is resident, they may pay, let's say $20 a unit. If they are non-resident, their tuition might be higher, so they may pay $50 per unit or something. Whatever the number is can be added in the residency table. Then we have a table for the college itself. So this system can be used for multiple colleges. This is how we are trying to set up. So a college can have ID, name, address, telephone number, and you can see that each table has its own primary key, which I've named as ID, and it's consistent across all tables. The next thing is the department table, which is a child of college. Department table is the child of college. So college can have multiple departments. So it has name and location. So location will also end up being a foreign key. So a table that has foreign keys often is referred to as a child table. Okay? So that's department. Then each department can have courses. So some of you were asking the question on how do I differentiate between a course and a section. So that will be described right now. So course is, as a table, it will have an ID, it will have a course number, course name, prereq, and department ID. So oftentimes people say, well, what's the difference between an ID and a course number? So ID is just going to be a unique integer value. And course number is a unique value that is assigned by college. So if I take you guys to our website, Dianza's website, right? So we go to our course catalog. So you'll be able to see there is a CRN number 44023. So across departments we've got these different course numbers. We also have the course name, like SolidWorks beginning. And when we start talking about this information, start date, end date, start time, end time, who's teaching the course, the location, all of this information will go in the section part in a moment. I'll describe that. So that's where we take the course info. Okay, and then department ID is a foreign key. So we can separate out different courses or courses for different departments. And then we have sections. So section, as you can see, is the child of course, instructor and location. So when I end up defining a section, it has a ton of properties. We have ID, we have a section number. Section number is like in our course catalog here, you can see DMT-60A-01, -64Z, those are section numbers. Like 61 is the section number. Anytime we have an online class, we tend to make that section 64, and then we use a letter like Z or A or whatever. So the point is that depending on the requirements, each college can come up with its own section number. Now we have to say, well, this section is for which course? And that's where course ID comes in. Where will this be taught? So give me the location ID so I can define the room number, if you will. And then the start time, end time, start date, end date, and then the user ID. User ID I'm using here because I want to associate the instructor to the course. I want to associate the instructor to the course. Okay. Then we have, once the section is defined, this will require doing a few joins. I mean, how many foreign keys do we have? That'll be the number of joins we'll have to do if we end up selecting columns from those tables. So at least 3 joins. Then we have student registration table. This is full of foreign keys. So when a student registers, there is a ID, and for each registration, I want to say which student is taking which section and how did they pay for it. That is how in student registration table we will track the registration classes a student may have registered for. So that's going to be a physical table. And then we have a catalog. This is going to be a view where that is created. That's going to be a query that's going to show a college catalog. So basically something like this. Now I'm not saying that you have to produce a HTML page showing the catalog, but you'll end up writing a query that will have all this information. So, okay. That's the catalog. So then we go through defining the relationships. And this is where I begin to gave you a starting point for defining the cardinality. And what I'm asking you all to do is complete this. So look at all the tables that are defined above and help me define the cardinality or complete this part. Like which parent, each time a parent has a foreign key, define if it will have 0 or more or 0 or 1. So define that relationship. Once you're done with that, then you have to do what is called a chronotation. And chronotation is a representation that we are using for describing the schema. Now, to give you a starting point for, so I guess I should copy this also in the notes. So diagramming, use the chronotation PowerPoint. So let's first look at it in the Intro to RDBMS doc, how the chronotation is done. So it's clear. So here is one example. We put the name of the entity on the top. We put all the columns, column names, and then we use these characters to represent something. So hash means that it's a star means it's required and hash means it's primary. It's a unique identifier. So that combination of a hash like this pound sign and the asterisk represents a primary key. When a column is just required, like it cannot be a null, it cannot have, if it has a not null constraint, or it cannot be, if the value cannot be null, then we put an asterisk there. And if it can be null, then we put it, the value is optional. And when we want to set up the cardinality between entities, then we use this crow leg. That's why it's called crow notation. So in this diagram, we can say that one department can have many employees, but it's okay if an employee does not belong to any department. So department number column the value can be optional according to this representation, because we are using a dotted line. So then the next thing is, well, how are all the relationships represented? So, here is a legend that describes the different ones that I talked about earlier. Like a single line is going to represent one side of a relationship. If I want to say one to many, then I'll use the three-legged crow leg to represent that. And then we have 0, 1, and then 0 to many. So to help clarify how these relationships are represented, here is a total list and a graphical representation. And the nice thing to do next is to see how this is in fact used. So in this case, we are saying that we have a relationship between authors and articles. So when we represent a 1 here, we are basically saying an article must have at least one author. And then when we say authors to articles, so author may not have any articles, or they may be an author for multiple articles. That's why 0 to many. Once these relationships are set up or defined for your schema under this part, then diagramming it would become a lot easier, in my opinion. So then to learn how to diagram and where to do it, I have provided you a starting point on the website with this crow notation practice.ppt. So there we are. So what I'm looking for in the schema at the end of the day is the name of the column and the data type that you all are going to use for a specific call. And depending on how you define these in Lab 6, Lab 7 will end up using this for actually creating the tables. So I'm going to talk about the DDLs, or data definition language, next time, I think. I'm not going to get to it today. But you have to be very careful with the choices of the data types. There are only 3 data types that you can use: number with a value, varchar 2, and date. Unless you're trying to save an image of a picture of a student or an instructor, which I'm not requiring you to do in the schema yet, then we don't have to worry about those. Okay? So you can see how the primary key is set up, how the required key is set up, and how the foreign key is set up. So I can use a hash with 2 brackets inside a bracket to represent a foreign key. And I've also given you a floating crow leg to plant wherever we need it. And the font size doesn't have to be this large. You can fit all of the schema on one slide. So you can reduce the font size. I will zoom in and take a look. So even if it's in font size 4, it's totally fine with me. So please use this as a starting point and make sure that when you deliver the schema that you include the data types in it. And your deliverable is just this crow notation diagram, and that's it. And actually I've started some work for you all, but go ahead and complete this table and then submit that for your homework. Fine. Any questions? So this is preparing for Lab 6. That was a lot, right? So we're going to go into, what we're going to go into next is DML statements, which I believe is a topic I haven't covered. Right here. So this is a starting point of like doing inserts, updates, and deletes. Let's take a short break, like for 3 minutes, and we'll resume with this topic. So the next segment we're going to focus on is learning how the DML statements work. And that is looking at DML stands for Data Manipulation Language. And we have dabbled a little with this as we were working on the select statement. So we're going to look at insert, update, delete insert, update, and delete statements and see how these work. So in fact, you'll find that these slides are very comprehensive and I would say kind of self-evident, if you will, because they are written fairly well. So you can add, modify, or remove data from the database using DML. And because data view has to be consistent in the database, it uses a notion of a transaction. So, for example, if 3 users are concurrently modifying my salary, and let's say I'm getting 3 raises in one day concurrently for some odd reason, each user will have a separate transaction, and each transaction will be updated and it will be its own unit of work. So the point is that if my salary changes from $100 to $105 to $110 to $115, each person doing that update will keep that value. I mean, they'll be able to have their own consistent view of the data. They'll say that 100 changed to 105, and yes, it's complete. And then we can go to the next step of the update and so on. So there are 2 parts to this lecture. One part is learning the syntax and its effect, and then having a light introduction to the concept of a transaction and its properties. So that's the twofold knowledge that comes out of this particular deck. So when we insert a new row into a table, we are using the insert statement for that. And we can only add one row at a time. That's the, I guess, limitation. So the syntax, the way it works is we say insert into table, and then we have all these columns, right? So anything that is in rectangular brackets is optional. And you can specify the values. The values have to match the data type of the columns. And the way to describe the data type of the column is to just use the describe command in SQL class. So if I describe a department, I get department number, department name, and location in that order. Generally, describe will show the column order in the way it was created. So when I have a create table command, if I define department number, name, and location in that order, that's what will show. So specifying the column names is optional. So if I don't specify these column names, I can just define the values, as long as I define the values in the order the describe shows, the describe command shows. If I'm using strings or date values, I should include those in a single quote as shown. We can also insert null values by not specifying null. So if you omit a column, that implicitly is a null. If you don't omit a column, you can specify the word null. If I'm trying to insert today's date, then I can call the sysdate command. You guys, or the sysdate function. You're familiar with some of the SQL functions already. So I can just use the sysdate command, and I can just say the person, especially if I say the person was hired on the day the row was inserted. So, and then we can also use toDate function to format the data a certain way. I would recommend trying these out. If you actually don't end up trying these out, this is what Lab 8 is all about. So you'll eventually end up doing it anyway. And one of your best resource for understanding the DMLs is looking at the script that we used in Lab 1, because that has a bunch of these insert, update, and delete statements that, or maybe it might have a lot of inserts. So you can look at that for your knowledge sake. We can prompt the user. Remember, when we talked about formatting columns, we talked about we can prompt the user to enter a value, right? So that's using an ampersand. So you can do that. You can also create scripts using this accept and prompt command that we have talked about before. So in my opinion, this is a repetition. We went through this, I think, 2 weeks back before the midterm on how to format data. It was in this topic. demonstrate how formatting output works to produce readable reports. So please look at that video for more information. We can do an insert as select. So if we wanted to copy a bunch of rows from one table to another, then we can do an insert as select, as you see here. In this case, when we do a select, we are going to end up copying the tables rows from one table into another. This insert statement assumes that the managers table already exists. So matching the number of columns and their respective data types in the subquery is very important. And you guys, I think, are now familiar with the concept of subqueries, so this should be pretty easy. When we change the data in the table, in this case, we want to change Clark from manager from department 10 to 20. For that, we will do an update. So you can modify an existing row with an update statement. As you can see in the syntax, we say update table and set column values with a where condition. If we don't have a where condition, what happens? You end up modifying the entire table. So even though where is optional, most of the times it has to be used unless you're changing something that's in the entire table. Here is for employee ID 7782, changing the department number from whatever it is to 20. You should do a select before and after to verify before making the change permanent in a transaction. So if you don't use the where clause, then all employees will be added to department 20. That would be a bad idea now, right? So be careful with the updates. That's why in most environments there is a test database and a production database. So you don't make those changes in production directly. You go through a change management process to make those changes. Here is doing an update using a subquery. So we are saying let's update the employee 7698 to the same department ID of 7499. So that's a correlated query. If you remember from lab 5 or lab 4, I'd asked you what a correlated query is, and when you compare it to something. So in this case we are saying what? Let's find the department ID of employee number 7499 and set it for 7699. A correlation. So again, same thing. Updating rows based on another table. Using a subquery in both set and where. So we are looking at department number of 7788 and job of 7788 and updating the employee table. We are updating, we're setting the department number based on the job. These correlations are of course always interesting. One of the things with insert and update we are going to run into is you're going to see integrity constraint violations. So this you'll always see when you try and update a column where a specific value may not exist. Like if I am updating a department number in employee table with a department number that does not exist in the department table. Or if I end up adding a duplicate value. If I end up adding a duplicate value in a table, like for the primary key, I use a duplicate employee ID. That will also lead to an integrity constraint violation. And those are best managed by looking at the data that is in the database and figuring out what values you have and don't have, and adjusting your insert and update statements accordingly. Next thing is removing data from a database. And that we use the delete statement. So if we want to remove our department, we'll get integrity constraint violations with this too. If I remove a department that has employees, then the database will not allow me to delete. Remember the usage of both primary key and foreign key? That shows up again here. Okay? So delete is, you can say something like this. You can delete a row from a table, or you can with a where condition, or you can just delete everything by just saying delete table. So delete table will actually remove the table itself. It will remove all the rows from the table and delete the table. Then you have to, well, the table will still exist, excuse me, but it will remove all the rows from the table. So how does delete work? Delete from department where department name equals development. Or delete from department. Then you can see the number of rows that are deleted with and without the where clause. This is again bringing in subqueries, which I guess is a pattern in the slide deck with using queries with insert, update, and delete. So we can use subqueries to remove the tables based on values in another table. So in this case, we are removing all the employees by finding the department number from the department table. And we can still see those integrity constraint violations as I spoke of earlier. If there are employees associated and you're trying to delete a row in the parent table, then you'll see this. So the next topic is on transactions, and I think I'm going to be able to do a very light intro to this topic. 5 to 7 minutes won't do justice to this topic for sure. So we'll talk about transactions in more depth to illuminate this idea in your head of how transactions work. So transaction is a unit of work, and in a nutshell, the DML statements, every time a DML statement is created, the database sets up a transaction in the background. And what a transaction does is it basically creates a separate work area for whatever our insert, update, or delete is going to do. It sets up a separate work area, separate memory area, so the master copy of the data is not impacted. And the goal is that a consistent view to the data is provided by by a transaction. So it's used with DMLs, DDLs, and DCLs. DML is insert, update, delete. DDLs, as you will learn, are create and alter statements, which we'll talk about starting next week. And data control language is statements that are used with transactions. So more specifically, looking at commit and rollback, so we can control the state of a transaction. So a transaction begins with the first executable statement, and it ends with either commit or rollback. With DMLs especially. DDLs and DCLs, it automatically commits, or a transaction also ends when the user leaves the session, or if there is a system crash. If you exit the system without committing the data, then the likelihood is that the data changes you made will be lost. So for example, if I changed the employee salary from 100 to 200, and I did not commit that change, next time I come back, I'm not going to be able to view that change. However, if I do a commit, then it will update the master copy, and I will be able to view the change. So a database transaction with commit or rollback ensures data consistency. You can also preview the data before making it visible to everybody. And the idea of a transaction is that if I wanted to group certain operations for users, I can do that. So I can group logically related operations inside a transaction. So this will give you a kind of a visual that, let's say within one transaction you do an insert, then an update, then an insert and a delete. You can take all of these ideas and put them in a single transaction. And what you can do is, after set of these DMLs, you can create save points, which is basically a logical pointer saying that, a logical marker saying that my transaction has gotten to a certain point. So I can call each save point, I can give it a name, and that way, if I end up doing that, if I have to roll back, I don't lose all the work. I can just roll back to a specific save point and be done with it. Right? So implicit transaction processing. So when we work with DDLs and DMLs or DCLs, there is a implicit commit and or a rollback. So what we do is, when we are ready to commit the data, we'll just go back and make sure that any changes we have made are accurate using a select statement. Before the commit, any changes you have made are not viewable by other users, and generally the affected rows are locked, and other users are not able to change the data. So let's say if you're modifying the salary and there are two users going at it at the same time, there's only one user that can update at a time. So that will slow things down a little bit in a inside a database because changes are made by one user at a time. And once the data is committed, all these 5 things happen. The master copy is updated, so the data is viewable to everybody, and the previous state of the data is lost, and all users can view the results now. And there are different types of locks that are set up that are now removed, and all the save points are erased. So the question is, how does commit work? We have an update statement or an insert statement that you add, and you can write a bunch of those. You can also create save points in between. I'll show you that in a minute. And then we just use commit and we're done. And this is how rollback works. If you accidentally said delete from employees, meaning you deleted the entire employees table, data in the employees table, you can do a rollback, so it will bring or restore all the changes back into the database. If you end up making such a mistake, don't commit because you'll have to reinsert all the data. We can roll back to a save point. So let's say you do an update, you create a save point. You do an insert, you update the previous save point, right? So you can go back and do a rollback, and that way you don't lose all the work that you have done. You can in an interactive session save some of your work. I generally don't do inserts and updates in an interactive session. I usually like to write scripts and run those scripts, which will be the case you guys will end up doing in Lab 8. So we basically do either a commit or a rollback or use the save point. That's the point of the rollback. And we're going to spend a ton of time talking about read consistency in the detailed, when we have a detailed discussion on transactions. So today was more how you use SQL Plus to control a transaction, and we are going to look at the theoretical view of a transaction on next week, and we'll have more detailed idea of how these work. If you guys have any questions, let me know. I'll stop here for today, and I'll post the video sometime soon, later today once it's ready. I do upload the video at the same day usually, unless I'm away from a computer for whatever reason. So it does take a few hours to produce the video. So it can't be instantaneous with unless I'm doing like a live YouTube, which also takes a couple hours, by the way. So anyway, have a great rest of the day, and I'll see you all next Tuesday, same time, same place. Take care, everyone.